So the big thing with physics is that, okay, we're talking about, in mostly for us, the movement of objects, the movement of systems, okay, kind of looking at how they move, why they move, and for anything to move, there has to be energy involved. Okay, so we start off this unit looking at all the different kinds of energy. We don't deal with all of them, right? We deal mostly with mechanical energy and things like that, but we will go over all the different types kind of as an introduction to this unit, because energy governs basically all things physics. It also governs all things chemistry and all things biology, okay? But that's kind of something for another time. So if we're looking at kind of examples, okay, one of the examples they have in this book here is that if you go, like, the Inuit have this ritual thing that they do called the Inuit blanket toss. Okay, its origins come from methods of hunting that they used to use way back when. In the tundra where they live, it's basically a frozen prairie. Okay, there's like no trees. It's very, very flat. Okay, you can see for a long ways, but it also makes it difficult to sneak up on any prey. Okay, like like a caribou or something like that. It's hard to sneak up on them because there's no cover anywhere. So in order to kind of get the drop on prey animals, what they would do is take a blanket. Everybody would stand around and grab a hold of the blanket, and they'd put the smallest person on the blanket, and they'd throw them up in the air as high as they could. Okay, because by throwing them up in the air as high as they could, it's like climbing a tree to see farther, right? So these people they'd be up in the air, they could see past the horizon a little ways, then find if there were any like caribou or any other animals that they could kill and eat, okay, without that animal necessarily seeing them or hearing them in advance of them getting there. So it was actually used to help them hunt animals and things like that. In order to get this person to fly up into the air, what does everybody holding the blanket have to do? Pull. Okay, they have to exert a force. Okay, when you exert a force that results in someone moving, you are doing what we in physics refer to as work. Okay, very simply, work is a physical term, meaning to change the energy of something. Okay, so to throw someone up in the air, we're converting all kinds of energy into different kinds of energy. We never create energy, we never destroy it, but it's very easy to convert it from one form to another. So we got all these people holding on to the blanket. Okay, the energy in their bodies is chemical energy, the food that they ate. Okay? As they use their muscles to pull on the blanket, they convert that chemical energy into mechanical energy, as well as some heat. That's why when you work out, you start to sweat, you build up heat. Okay, so they turn that chemical energy mostly into mechanical energy that moves the blanket, okay, and transfers energy to the person sitting on it. All right, so the person sitting on the blanket gains energy and as a result moves very, very fast and flies up in the air. As they fly up in the air, their kinetic energy, that is the energy that has to do with how fast they're going, is gradually changed into potential energy as they move upwards. Okay? Because at their highest point, how fast are they moving? Well, actually, they're instantaneously, at least for one instant, stopped. Okay? You throw anything up in the air, it goes up, but it slows down, it slows down, it slows down, it stops at its peak before falling back down. Okay, so all the energy that the people throwing the blanket or using the blanket have put into it, okay, becomes kinetic energy, then becomes potential, and then when they come back down, turns back into kinetic. And if they don't want to kill that person, then they need to catch them and slowly decelerate them, which means now they're going to kind of do some more work in order to slow that person down and to break. Okay. All right, so we got to look at what are some of the more common forms of energy. Before we can do that, we got to look at what really is energy. And that's not a small question. In fact, it plagued scientists for a very long time because energy is not something material. Okay? It's not like matter. Matter is everywhere. It takes up space. It has volume. Okay? We can see it. We can touch it. We can move it around. That is not true for energy. Energy is not material. Okay? While we can sort of feel heat, I can't grab heat and go, okay, I've got all this heat in my hands, I'm going to move it over here. Okay? I can't do that. It's not matter. Right? So it was hard for people to explain what energy was and how it worked because it wasn't something they could contain or measure or quantify. Okay? All right, so essentially, like a very simple definition of what energy is, okay, is that it's the ability to do work. Okay, so we have a definition of energy. Okay, energy is the ability to do work. Okay? Because work is a transfer or change of energy. I can't give away what I don't have. So if I don't have any energy, I can't do any work. Okay? It's the same argument that you might try on your parents, after a big snowfall, and they say, hey, go out and shovel a walk. And you're like, oh, I have no energy. I can't do that. Of course, you're lying because you have energy. If you didn't have energy, you'd be dead. Okay, but you don't really want to. If you technically didn't have any energy, it would thus be very difficult to go out and shovel the driveway. Okay, so energy is the ability to do work. If you have it, you can. If you don't, you can't. Okay, so typically when we think about energy, what we think about or what we visualize is the forms of energy that are familiar to us. The sun, okay, electricity, like an arc of electricity, a lightning bolt, okay, things like that. All right, so we know that a person who has just run a marathon has used a lot of energy, okay? We only see the evidence of energy when something is done, okay? You can't really see energy in and of itself. All right, so when we see like a flash of lightning, we are seeing the electrical charge that is being transferred from one place to another, also being converted into light. And a few seconds later, sound as well. Okay? All of those are forms of energy. All right, so it's not surprising that the development of the idea or concept of energy went hand in hand with our development of technologies that use it. Okay? In fact, this is one of the examples of a time when we designed a whole bunch of technology that used something we didn't fully understand. Okay? We didn't really have an idea or a concept exactly of what energy was, yet we were building all sorts of machinery to utilize it, convert it, okay, and do things for us. All right, so by the 1850s, scientists were convinced that there was this idea of or concept of energy, but energy was difficult to describe because it was only an abstract idea, and again, as I said before, not a material object. Okay? Experimental evidence supported the theory that heat was just another form of energy, and it could be converted into other forms, which we do all the time. Okay? When we burn any fossil fuels, we get heat, and then we use that heat to do something else. All right. If we're talking about generating electricity by burning coal, okay, which is something we do a lot of in Alberta, okay, we are turning that energy into heat, which we are then transferring to water. The water is vaporized, and then the steam turns a turbine, which generates electricity. Okay, so we're using heat to do something else. Unfortunately, using heat to do other things is probably the least efficient way to do anything. But heat is also the most readily available form of energy. Okay? The same thing is true in your car. When you burn gasoline in your car, okay, the gases get hot and expand as a result of the ignition of gasoline. Okay? Expanding gases in a confined space, the cylinder of the engine, moves the piston up and down, okay, which allows the car to move and do work. But again, it's turning heat into other forms of energy, which isn't really efficient. All right, so we had some scientific breakthroughs that occurred, okay, and scientists realized that other physical phenomena in science might be explained by this idea of energy, okay, and that other forms of energy can exist. So we'll talk first here about our most common form of energy, and that is chemical energy. Right? Chemical energy is the energy that is stored in the bonds of any chemical. Right? Very commonly, we use this chemical. Okay? This is C3H8. You might recall it back from the chemistry unit. It was often involved in this kind of a reaction. Right, involved in a combustion reaction. That's an H. Okay, so it's involved in a combustion reaction. That's propane. Okay, when we burn propane, what we're doing is breaking all of these bonds that join the atoms together. Okay, energy is stored in those bonds. When those bonds are broken, the energy is released as heat. Okay, that's how the burning of all fossil fuels works. Okay. That sort of makes sense? So we're using, it's essentially chemical energy is a form of potential energy. Okay? Anything that has energy stored in it that can be released later is a form of potential energy. So chemical energy is a form of potential energy. All right, so early alchemists, okay, we talked about those guys in the chemistry unit, okay, realized that some reactions contained what they called hidden secrets. That was, they could blow themselves up if they weren't careful with them. Okay, and that's where essentially this idea of chemical energy kind of came from. Okay, while they tried to make gold by mixing all the elements they knew, the alchemists began to discover that mixing certain chemicals could produce surprising / dangerous results. Okay, the science of chemistry began, but it wasn't until the early 1800s when the two guys we talked about, Lavoisier and Bacon, came up with the scientific method. All right, so when wood burns, okay, the cellulose molecules, okay, the energy in them gets released, right? So when you burn wood, essentially you're taking some sort of hydrocarbon and you're breaking all the bonds, releasing the energy, okay? So it turns into heat, and that's the evidence that there is energy in the chemical reaction, right? So chemical energy is the potential energy stored in the chemical bonds of compounds. That includes the food that we eat. All right, your mitochondria, okay, the little things in your cells that break down sugar for energy, that's the exact process that they are doing. They're breaking the bonds in the molecules of the sugar and food that you eat and releasing the energy to help you out. Okay, chemical energy, most readily available form, at least for us. Essentially, all modern society is driven by chemical energy. Okay? It always has been. Hopefully, it won't always will be, but okay, certainly it's readily available and quite cheap. Okay, especially here in Alberta, where we have lots of access to coal and oil and gas. Okay, and it's a great way for us to make cheap energy. All right, next form of energy, okay, has to do with electricity and magnetism. And we're listing these two together because they're quite intimately related. That is, one usually causes the other. Okay, moving electrons can actually produce a magnetic field, okay, and thus magnetic forces, hence how an electromagnet works. Right? So electricity or electrical energy is the work done by moving charges. Okay, so when we charge up our phone, right, what we're doing is putting energy back into what is usually a lithium ion battery. Okay, so we're putting electrons or putting them kind of back where they belong, okay, or back in a high energy state. And then when we turn our phone back on or start using it, those electrons flow from the battery, the high energy state, okay, through the phone, and they do all the work by transferring some of their energy. So essentially, as they go through your phone, they slow down a little bit. And when they're slowed down, some of their energy is transferred to the, the microchips and the processors and things like that, the screen and whatever in your phone, allowing it to do its job. Okay? When they come out of the phone, they have less energy. Okay? And eventually we exhaust the energy in the battery of our phone. Right? We plug it back in, we put that energy back. That sort of makes sense? But it's those moving charges that allow work to be done. So when a battery is dead, okay, at least that's what we call it, when it won't do any more work, there's still energy in it, but not enough for the charges to flow from the negative side to the positive side. Okay, and that's the way they go, by the way. Okay, it goes from negative to positive. Right. So if there isn't enough, if they don't have enough energy to flow, then they obviously can't do any work. They're still there, okay, but they're not able to do much work anymore. So the first battery was made by a guy named Alessandro Volta, an Italian scientist in the early 1800s. Okay, it was called the Volta pile. Now, that is where obviously the name for modern batteries comes from. If you ever look like on an Energizer, Duracell, like any kind of battery, it'll say alkaline pile battery, okay? Because it is, okay, kind of the offspring, or this idea here was the distant ancestor of the modern, like AAA or AA battery. Okay? It's a pile of individual kind of cells. All right, so essentially what Volta did is he discovered that if he had layers of different kind of metals with moistened paper in between them, there ended up being kind of a potential difference in electrons between them. And if he put something in the middle, he could see that the electrons would flow through it. All right, and so that was kind of gave him the idea that electrical energy could be stored in a solid form and then released when it was hooked up to a circuit. And that gave him the idea for the first battery. Okay, so Alessandro Volta, okay, essentially developed a device that constituted the first battery. Now, it also showed that you could convert chemical energy, which is what's stored in all batteries, into electrical energy. Okay? A battery doesn't create energy, it converts it from one form to another. Okay, can you recharge a standard alkaline battery? Actually, you shouldn't. You might be able to maybe once, but it is not an advisable idea. Okay, non-rechargeable batteries, you should not attempt to recharge. They are chemically different than rechargeable batteries, and as a result, the chemical reaction that produces electricity in them is not reversible. So what will end up happening is you'll start putting electrical energy backwards through this thing, and you can't reverse the chemical reaction that has already occurred, so heat will build up in the battery to the point where it could start a fire or even explode. Okay? If you are using a rechargeable battery, they usually contain different chemicals, okay? Usually lithium ion type batteries. Okay? But non-rechargeable batteries, you should not throw in a charger and attempt to recharge. You will very likely start a fire. Yeah, attempted to do it. It's not a good idea, okay? It really just does not work very well. All right, so once this was developed, okay, then once we could get like kind of current to flow, okay, get electrons to move, we discovered that when they moved, they did stuff. Not just work like powered electrical devices, but they also produced magnetic effects. Okay, so Oersted and Faraday, two separate scientists, discovered these magnetic effects of electricity. Okay, and Oersted, okay, in his experiment, he actually discovered this by accident. He was doing some stuff with magnetism, and he had a circuit running at the same time. So he had a compass there, and he discovered that the compass wasn't pointing north. And so he picked up the compass and picked it up to look at it, and then it pointed north. And then when he put it back down underneath this current carrying wire, the compass lined up with the wire. Okay, didn't point north, it lined up with the wire. If you picked it up and moved it away from the wire, it pointed north again, right? Well, a compass responds to magnetic fields most of the time, the magnetic field of the Earth, because it's bigger than anything else around, okay? But as soon as he got it close to the magnetic field produced by the moving electrons, it would alter and follow that one instead, okay? So he discovered that electricity can produce magnetic effects. Okay, that is that electrical energy can be converted into magnetic energy. Right? And this is now what we use to produce electromagnets, okay, as well as like transmitters and receivers. Okay? The magnetic effects of transmission electromagnetic waves can be converted, okay, from electricity or to it. All right, so that was Oersted's thing. Okay, so we should probably know who Oersted was. So Oersted discovered, okay, that an electric current in a wire would produce a magnetic effect. Okay, by accident he passed this metal wire, okay, over a compass and noticed that the compass moved in response to that. Okay, now Michael Faraday, on the other hand, discovered that the reverse was also true. That if you had a magnetic object, it could push electrons around. Okay? So he discovered by making a coil of wire that he could move the electrons by forcing them to go away from a magnet. Okay? So he made this coil of copper wire and then put the magnet into the coil. And as he moved the magnet through the coil, the electrons would move away from it through the wire and create an electric current. Okay? This is essentially how a generator works. A generator can move a magnet up and down through a coil of wire, producing alternating current. Moving towards, moving away, alternating current, okay, or AC, the stuff that we use all the time. All right, so that was Faraday's contribution here. So Michael Faraday, okay, showed that the reverse could happen, okay, magnet through a coil of wire, and that caused electric current to flow through the wire. All right, so people are starting to get this whole electricity and magnetism thing figured out. And then some people said, is there a way for us to convert other forms of energy into electricity? Okay? And they discovered that, yes, there were. They're not terribly efficient, but there are ways to do it. Okay? And the first guy to try that was a guy named Thomas Seebeck. Okay? Thomas Seebeck discovered you can convert heat directly into electricity. It is horribly inefficient. It's not something that we would generally use to make electricity, okay? But it can work. right? He developed what's called the first thermocouple. Okay? A thermocouple turns heat into electricity. So what happens is, okay, he had these different metals. He had a bar of iron, and then he had this copper kind of horseshoe-shaped piece of metal, okay, above it, and then he had a compass needle in between. Now, metals heat up at different rates, and when you heat something up, what happens to the molecules in it? Well, the molecules don't expand. The substance might expand, okay, and the substance expands because the molecules are moving faster. Yeah, the hotter they get, the faster they move. Okay, but because they heat up at different rates, the particles in one of these metals were moving faster than the other. Okay, and as a result, electrons started to flow through essentially what became a circuit. Right? So even though neither one of these things had any electrical energy or chemical potential energy, he was able to use the kinetic molecular energy of moving molecules to produce an electric current. He knew he was producing an electric current because as soon as he started heating this up, the compass needle pointed along the bars instead of north. Okay, so he knew he was creating electric current because he was producing a magnetic field. Oh yeah, electricity turns into heat easy. Yeah. Okay, we do it all the time. Like your toaster, your oven, your hair dryer, your like anything that we use to heat, any kind of electric heat device, right? All right. So, like we said, Seebeck produced the first thermoelectric converter or thermocouple. Now, like I said, it's not a great way to generate electricity, but it is useful in protecting electrical equipment. Thermocouples are often used as circuit breakers. Okay? If a circuit begins to get hot because of the amount of electricity flowing through it, it can generate its own electricity, enough to pop the breaker in that circuit and protect the circuit from overheating. Okay? How many people have ever had to go in their house down to the breaker box and flip something because it popped? You ever done that before? Really? Holy smoke, you guys haven't lived. Okay? You never overloaded a circuit? Yeah, your circuit breaker. Yeah, the downstairs, you just flick the switches. You should probably learn how to do that. It's important. Eventually you'll do it. Usually it happens if you plug too many things in on the same kind of socket, right? So if you have like a big power bar and you've got your toaster and your microwave and a whole bunch of stuff all plugged into it, you'll pop it. You're just going to draw too much. It'll make too much heat within the wires and the circuit breaker will pop, okay? And the reason for that is if we don't want the wires to get hot. If the wires get hot, we can start a fire. Okay? So circuit breakers essentially prevent electrical fires in your house, okay? And they use essentially a thermocouple to do that. Okay? If enough heat is generated in the circuit, it will result in a small current that will pop the breaker. Yeah. Yeah, exactly. You get too much stuff going through there and it just pops. All right. Okay, nuclear and solar energy. Okay, we had a total misunderstanding of how the sun worked for a very, very long time because people would look at the sun and go, "Oh, that's really bright," and then you'd see spots. And okay, but it looks like a big fire, right? Like when we see kind of videos of the sun, that have been filmed or whatever, it looks like a big giant fire, and it is. But people for a long time didn't realize there's different things that can cause fires. Okay, not all fires are chemical reactions, but that was what everyone's experience was. You only get fire when you're burning chemical energy. But the sun is a nuclear fire. Okay? It's much, much different. Okay? It is the result of forcing atoms together in a process called nuclear fusion. We talked about that actually back the very first day. Okay? We talked about nuclear fission, which is splitting an atom, and we talked about nuclear fusion, which is forcing them together. Okay, so it was 1896 when Henri Becquerel discovered that certain atoms spontaneously disintegrate. Okay? That is, they just break down. They're not stable, and they break down and turn into other things. The atoms actually physically break. Okay? Uranium does this, plutonium does this. Okay? All the essentially radioactive materials, okay, will break down on their own. Okay? When they did that, they emitted radiation or radiant energy. Unfortunately, people didn't realize around this time that that stuff was bad for them. Okay? And in fact, they have Henri Becquerel's desk in a museum, and it's behind lead-based glass because it is still hot, radioactively hot because he had all these lumps of radioactive material in his desk because that's what he was studying. Okay? People at the time didn't realize that if you played around with that stuff, you would get cancer. Okay? That's essentially what being exposed to all that radiation would do. A lot of the people who worked in like molecular or atomic physics at that time did not live to be very old. All right, because most of them were exposed to high levels of radiation because they didn't understand that that stuff was present. It wasn't something they could see. They'd just go home from work and be like, "Oh man, I don't feel very good," okay, and have that slight greenish glow. Not really, but okay, they would be exposed to all of this radiation in the workplace. Mary Curie is another one, right? She died very young. She was working with lots of radioactive materials. People just didn't know it was bad for you, okay? But yes, she was. Well, she discovered that she did similar work to Becquerel, but after Becquerel. Okay, so pretty sure it was after Becquerel. Anyway, they discovered that they emit this stuff. We didn't realize how bad it was. We knew they emitted certain types of radiation, but we didn't understand things like X-rays and gamma rays and things that are really bad. Okay, so that led to the development of a new source of energy, nuclear energy. Now, nuclear energy is a form of potential energy, okay, and it's stored in the nucleus of the atom. If we alter the nucleus of the atom, then we will release nuclear energy. Okay, and there's essentially two ways to do that: nuclear fission, okay, which is when an atom is split, okay, or when two atoms combine, it's nuclear fusion. All of our nuclear power is essentially done by nuclear fission. It's easier to control, it's lower energy, things like that. So it's just safer, okay? Not really safe, but safer, okay, than nuclear fusion. Nuclear fusion releases a lot more energy per kilogram of fuel. All right. So when we're splitting atoms, we're releasing the energy stored in there because we're breaking it up and the energy comes out. But when you force two atoms together, energy is also released because now you are altering the atom. You're taking two and making one. Okay? This is what happens inside the core of the sun. Okay? The sun is incredibly massive. All right. To give you an idea, Earth has a mass of 5.98 times 10 to the 24 kilograms. I know that seems pretty big, okay, because that's 598 with 22 more numbers after it, okay? But the sun is a million times more massive. Actually, several million times more massive, but okay, it's on the scale of millions of times more massive than the Earth is. Mass produces gravitational pull. And so what the sun's gravity is capable of doing, because it has so much mass, is that it can crush and force atoms together at its core. Okay? There's so much force there that it can force two hydrogen atoms to join together. Okay? And when they do that, they become a helium atom. In that process, vast amounts of energy are released. Okay? And that is the fuel that fuels the sun. Right? People didn't even start really looking for a reason why the sun fueled until they realized that if the sun was a chemical fire, it would have only lasted about 5,000 years given its mass. Okay, so if it was like a chemical fire of some sort of, like, let's say gasoline or something like that burning, okay, not only would it not produce enough energy, but it would have run out, okay, after, like I say, about 5,000 years. Nuclear power, however, can run for a lot longer. Okay. Okay. The other problem, of course, with having it be a chemical fire is that chemical fires don't burn in. They don't burn in space. What is there none of in space? Yeah, there's no oxygen. It's a vacuum. You can't make a chemical fire happen in a vacuum of space. So it just doesn't kind of work. All right. So solar energy, okay, results from a hydrogen-hydrogen nuclear fusion reaction, okay, with the release of nuclear energy. That is all forms of radiation. Okay, that's heat, it's light, like visible light, it's X-rays, it's gamma rays, it's plasma, it's all kinds of forms of energy, okay, that come to the Earth. Fortunately for us, the Earth has a very strong magnetic field because of its iron core, okay, and that protects us from the vast majority of the really harmful crap that comes our way from the sun. Okay, when do we see evidence of the Earth being protected? When do we see evidence of some of the sun's energy being deflected away and protecting us? Hmm? Okay, UV rays are things that actually get through and hurt us. Okay, well, what is some, like the ozone layer can absorb that a little bit, but there's actually another thing that you can visually see at night. Nope, you don't see them every day. Nope. How many people have ever seen the northern lights? Okay, seen the auroras? Okay, the auroras are caused by a bunch of high energy particles from the sun slamming into the Earth's magnetic field. Okay, and the Earth's magnetic field slows them down, turns their energy into visible light instead of radiation like gamma rays and X-rays. Okay, and that is evidence that we are being protected from the worst stuff, okay, coming from the sun. Okay. Motion and energy. So this is the stuff, the forms of energy that we'll deal most with, okay? And that has to do with like mechanical energy, potential energy, okay? The energy of objects due to their position or their movement, okay? So a group of English scientists watched Newton's cradle, okay? That's what this thing is called. You know, if you've ever seen like a metal ball, right? You move one and it just goes back and forth, back and forth. This nearly got Newton beheaded, okay? Because people saw this and went, "You're a witch." That's when Newton lived. Okay, everybody, if you did anything weird, you were a witch. Okay, so they said, so Newton said, like, okay, so I pull this ball away and I let it go, and the ball on the other side will fly up. Okay, people didn't like that, right? They didn't like anything they couldn't understand. So anyway, to keep his head, Newton had to explain and come up with this idea. Okay, so here's what I've done. When I lift this ball up, I'm doing work and I'm putting energy, I'm giving it energy because I've moved it away, and the earth will pull it back down in the same way the earth pulls you down if you jump off a chair. Okay, and so what happens is it hits this other ball, and the energy that I gave it travels through to the other side. And when it hits this ball and there's nothing to stop it, it flies up on the other side. Okay? It was enough. He had enough like reasonably thinking people to keep his head and not get beheaded for being a witch. Okay, but he still kind of got himself in a lot of hot water over this like seemingly harmless demonstration. And you have to consider the time in which he lived. Right? But it was this demonstration that came up with the idea of mechanical energy, or this kind of living force that was there. Okay, and that's actually what it was called for a while. Okay? This guy named Gottfried Leibniz, okay, talked about this living force, which we now call energy, okay, that can be possessed by certain materials based on things that have happened to them. All right, so in this, okay, he reasoned that there's two kinds of energy. Okay, kinetic energy, which has to do with movement, okay, and potential energy, okay, that anything raised above the Earth's surface would have. Because obviously, if something is above us, we naturally keep an eye on it because there's a possibility it could fall on our head. Okay, we know just intuitively that something perched above us has the potential to fall, and if it falls, it can do work. Okay, and work could be, you know, changing the shape of something like us, which would be undesirable. Okay. All right, so even though Leibniz never called it this, his ideas eventually became known as mechanical energy. So the sum of the energy of motion and position, that is kinetic and potential energy, is known as mechanical energy. We'll be dealing with that idea a lot, okay, in this unit. All right, questions so far on that stuff? Okay, why does an object raised above the Earth have the potential to do work? Like if I, you know, take this hole punch, okay, let's say it was on the floor and I put it on the desk, why does it now have potential energy? Okay, gravity will pull down on it, but only because what did I do to it? Right, I put work into it. To lift it and put it there required me to exert a force over a distance and change the energy of something that on the floor has no energy at all. Right? If this thing is sitting on the floor, it has no ability to do work. There's nothing that can happen that was result in this thing doing anything. Put it on the desk, different story. Okay? Now it could fall. Right? So it now has the potential to do something, but only because I gave it the potential to do something by doing work on it. Okay? Okay, so heat and energy, like we said, these two things people understood and had harnessed for hundreds of years before we really even understood what they were. Okay, so scientists were puzzling over what caused heat. Okay, the ancient Greeks had no knowledge of the concept of energy, but they speculated that about what heat from fire actually was. Okay, the atomists like Democritus, we talked about him before, thought that heat was somehow related to the motion of atoms, and they were right. Okay, we now know that when you put heat into something, that the molecules of that material will move faster. Okay, but it seemed ridiculous at the time because no one could prove it, no one could see them, and there wasn't any evidence that that happened. Now, a guy named Joseph Black, observed that when a cold object was placed in a cup of hot water, the object got hotter. Shocking, shocking discovery. Okay, we all know that. We all know that if you want to heat something up, you put it in something hot, okay, or you expose it to some other form of heat, okay? But in this case, it also told us about the direction of energy flow, okay? That is, you can transfer heat, but you cannot transfer coldness, okay? So if you are cold, it's because you lack energy. If you are hot, it's because you have lots. And once again, you can't transfer what you don't have. So you can't transfer coldness. Okay? If I pick up snow and I make a snowball in my hands get cold. But it's not because the snowball has transferred coldness to my hands, it's because my hands have transferred heat away. Okay? Now that transfer will occur until the two objects are what? Well, let's say it's not. Let's not say it's snow. Let's say I just pick up a cold piece of metal. Okay, that metal is going to feel cold until until it's the same temperature as my hand. Okay, energy will flow, heat will flow until there's no direction for it to flow anymore. Once they're equal, then the flow back and forth is equal, and there's no net flow from one to the other. Right? It's the same idea of your battery. Your battery might still have energy in it, but it's so balanced now that it can't flow from one side to the other. Okay, so his idea here was that, Joseph Black, okay, he kind of discovered this direction of energy flow, okay, but he decided that energy must be this invisible fluid. People really like this whole idea of invisible magic fluids because it explained lots of things, but because the word magic was in there, they didn't have to really justify how it all worked. Okay, so this idea that heat was a fluid actually persisted for a very long time, okay? Because it explained sort of how something could flow from one place to another, okay, just like water would. Okay, so they said energy is a fluid. Well, but to be a fluid, you have to also be matter. Okay, and there wasn't any matter flowing from one object to another. Okay, and the evidence of that was that if that was true, the masses of the two objects would also change as a result of transferring energy, and that didn't happen. Okay, so they weren't transferring anything material. All right, so anyway, his observations on the flow of heat became one of the principles of thermodynamics. In fact, the second law of thermodynamics tells us that energy always flows from a high energy object to a cold energy object, and that was Black's contribution here. All right, now he also kind of revived this idea that transfer of thermal energy from a hot object to a cold object is heat. So heat isn't so much a form of energy as it is a transfer of energy. So heat and work are both transfers of energy, but they transfer different kinds. Okay? So heat is a transfer of thermal energy. Okay? That's what heat is. Heat is a transfer of thermal energy. Right? So when you say, oh man, that thing must be hot, I can feel the heat coming off of it, you're sort of right and sort of true. You're actually feeling the thermal energy from that object transferring to you. Okay, so heat is a transfer of thermal energy from one place to another, where work, okay, is the transfer of mechanical energy. Now, heat and mechanical energy, okay? These two things are also quite closely related, and one can turn into the other, okay? Turning heat into mechanical energy is highly inefficient. Mechanical energy turning into heat happens all the time. Anytime objects are moving, there's going to be friction. Okay? And friction is always going to steal energy away, usually in the forms of sound, heat, and light. Okay, everyone kind of with me there? So, a guy named Benjamin Thompson, who later changed his name for some reason to Count Rumford. Don't ask me why. Okay? He became the Minister of War in Bavaria. His job was to supervise the production of cannons. Okay? To produce cannons, you essentially took a big hand-operated drill or bore and bored out a big lump of metal. Okay, so in the same way that you would drill a hole in something with a hand drill, okay, these people would take a big auger almost, okay, and they would drill through these lumps of metal to produce the cannon body, the tube that is the inside of the cannon. Okay, well, what was discovered by Rumford is that these guys every hour or so would have a coffee break, because they would put a teapot on top of the metal they were boring out, and while they were boring it, it would produce so much heat that they could boil water to make tea. Okay, it would produce the boring process. Okay, would produce so much heat that they could boil a tea kettle on top of the cannon. Now, where did that energy come from? Yeah, and yeah, the friction on the drill, and then that drill got its energy from the workers. Okay? So the workers' energy that was in their food became mechanical energy as they turned the drill, became heat as the drill moved inside of the metal lump they were boring out. Okay? So while they were boring out these brass cylinders, okay, he noticed that a huge amount of energy, okay, or heat was being generated in the bored metal. In fact, he could boil a kettle of water on the cannon. Okay? And he noticed that that supply of heat was endless as long as what was going on? As long as they were drilling. Okay, so Count Rumford also invented the coffee break. If people worked hard enough, they could boil a kettle of water and stop. Okay, and then they could have something, they could have coffee or tea. Okay. No, American. But then went to Bavaria. So maybe he was also Bavarian, I don't know. But yeah. All right, so the experiments of Rumford produced strong evidence that heat was not a fluid, because where would the fluid be coming from? Okay, there wasn't any fluid there. Okay, so he kind of got rid of Black's idea of this whole caloric fluid thing. Okay, he discovered that energy could turn from one form to another, specifically from mechanical energy, the movement of the bore, okay, into heat. Okay, so Rumford suggested that heat could be manufactured by the motion of the workers, and he was the first to realize that heat and mechanical energy were related. No, I just make that up. It just sounds funny. Okay, who knows? I mean, if you could boil a kettle of water, I mean, why not, right? You reward your workers for working hard. If they worked hard, okay, they could boil the water and stop and have tea. Okay. I probably wouldn't have wanted to work in there. It sounds like the working conditions in a place like that would be somewhat unpleasant. If you could boil a kettle of water on the cannon, then it had to be pretty hot in there all the time. Right? And you wouldn't want to go, all right, guys, we're going to take our break and lean up against the cannon, and you get like huge burns on your hand as well. All right. After that, okay, we had a guy named Thomas Young, who was an English physicist, okay, and he linked mechanical energy to this idea of kinetic and potential from Leibniz. Okay, so he had this idea that chemical and potential energy was present in moving objects. Okay, and so he thought that they could possess either one or the other, but in actual fact, you can possess both at the same time. Okay, an airplane flying through the air has both potential because it's above the ground and kinetic because it's moving. Okay. All right, so essentially then Young developed the definition of energy, okay, which is the ability or capacity to do work. Okay? It's the same idea that allows us to start a fire by, as well, the expression goes, rubbing two sticks together. Okay? If you you can't start a fire by rubbing two sticks together like this. It doesn't work, right? But a lot of the kind of the basic technique that was discovered by the First Nations people was if you had like a bow, okay, but you put a stick in it and twisted it, okay? If you put a rock on top of that stick and then move the bow back and forth, you spin the stick really, really fast. So if you put that stick on a piece of very dry bark or something like that, okay, there will be enough heat generated between those two pieces of wood moving past each other that if you had some really dry grass and leaves and things like that, a fire could be generated from that. Okay, so don't get the idea that if you just rub two sticks together, you're going to start a fire. You're just going to get tired and bored. Okay, but you could do it if you had kind of that bow set up. Okay. All right. Last guy, kind of most important guy here in terms of energy is Joule. Okay, the reason we say he's the most important, he's kind of the guy that put all of these ideas together and then proved quantitatively that yes, this is true, this happens, which is why the units for energy are named after him. Okay? The units for energy are joules. Okay? They're actually a kilogram meters squared per second squared, but we call them a joule, which is much easier than kilogram meters squared per second squared. Okay? Joule is much easier to say. All right, so Sadi Carnot, okay, he was an engineer. He did a lot of experiments that tried to transform heat into mechanical energy. So the opposite of what Rumford was doing. Okay, turning mechanical energy into heat is easy; it just happens, right? But turning heat into mechanical energy is more difficult. So he discovered that the transformation, so Sadi Carnot, okay, the transformation of heat into mechanical energy could only occur when thermal energy flowed from a hot object to a cool object. You essentially had to harness that flow of energy in order for that to happen, and it's not an easy thing to do. Okay, in that process, heat is always going to be lost to the surroundings, okay, and not be very, very efficient. The steam engine is more the expansion of gases, but it's along a similar line. Okay, all right. So James Prescott Prescott Joule, okay, proposed, properly substituted the term energy for this vis viva that Leibniz had come up with, okay, and he argued that heat was just a form of energy, okay, and he proved it, okay, using a couple of very simple experiments. These were Joule's experiments, okay. He used the falling block experiment to prove that mechanical energy, actually potential energy in particular, was real, because people didn't buy that. They're like, that object's not moving, it can't do anything except fall, right? So what he did is he took one big block and he moved it away, and he had a stationary block here that had a thermometer in it, right? All he did was release the block and let it smash into the second block, and the thermometer would go up. Okay? Same thing happens when you hammer a piece of wood. Okay, if you, like, not even with a nail, just take a hammer and a piece of wood and bang on it for a little while, then put your thumb where you've been hitting. It'll be hot. Okay? You're turning potential energy into heat. All right? So he essentially proved that because if an object was moved away from the Earth's surface, it possessed energy, and he proved that because he was able to measure it with a thermometer, okay, after the object had fallen. Okay? And his other one showed that you could turn kinetic energy into heat as well. Okay, so he had these falling masses attached to this spinning fan thing. Okay, so inside this jar, he had air in this spinning fan. So as these masses fell and the fan spun, the temperature of the air inside the jar would go up. Okay, the only place for the energy to have come from was from these falling masses. Right, so he was the one that kind of proved mathematically and measurably that one form of energy could turn into another, and thus these were actually forms of energy. Okay, so that was Joule's contribution. Okay, questions on any of that? Okay, so I think I have these circled in your notes package too, do I not? If I don't, they're circled on here. All right, there's a couple of questions here that I want you guys to answer. Okay, so question number 2, 3, 4, 6, 9, and 10. Okay, as well as 12, 13, and 14. Right? I'm looking for complete sentence answers here, descriptive answers, right? Things like that, because this is very likely the stuff that could end up on the first quiz of the unit next week sometime. All right, so all the answers to those questions can be found in the notes that we just went over. All right.